in this video, I want to go over quantum mechanics and valence electrons. So go ahead and get your notes out and see if you can follow along. So electron arrangement is going to be the first topic today. So quantum mechanics is a modern theory that states the following, that electrons and atoms can have only certain specific energies. We say that these energies of electrons are quantized. And whenever you think of quantized, think of staircases, okay? Staircases kind of go up like that. And so you might be in level 1, 2, 3, 4, so on and so forth. But that's what quantized mean. They're in discrete energy levels, okay? Electrons are organized into their energies into sets called shells. Generally, the higher the energy of the shell, the further on average it is from the nucleus, okay? Keep in mind we're talking about electrons. And so these shells are going to be 1, 2, 3, 4, etc. And here's your nucleus. So that might be shell 1, shell 2, shell 3, so on and so forth. These shells are then further divided into subsets of electrons called subshells, and this is where you get S, P, D, and F, as you'll see in the statement below. Just keep in mind this statement, the first shell only has one subshell, the second shell has two subshells, and so on. And they're labeled as S, P, D, and F. Different subshells can hold a different maximum number of electrons. For instance, S, you can only have up to 2 electrons, P, 6, D, 10, and F, 4. Okay. And so, posted in Unit 3, Unit 6, Unit 8, Unit 11, and Unit 15 is a black and white periodic table that is approved for you to take your exam with. It needs to be unmarked, so you're not allowed to mark it up, but you are allowed to print it and bring it to your exams. So again, those particular units, you'll find that periodic table that you need to print out and bring to your exams and quizzes. But here's where those subshells are located, okay? So your S is always going to be columns 1 and 2, okay? But keep in mind, we're going to take on helium right here as well. So those are going to be your S's, okay? Your P's are going to be pretty much everything that you would consider a non-metal right here. So those are your P's. Here's your D's, which are your transition metals for the most part, and then your F's are your lanthanides and actinides. And so if I'm asking you, as we're going to see later, to give me the electron configuration of aluminum, it's located right there. And so the way you're going to figure this out is you would start, and you have to get there, okay? So think of electron configuration as your house address, or a house address rather. It kind of tells you the identity of an atom based on the electron makeup using the quantum mechanic designations, okay? So you would say it's, and these S's or not S's, the energies or the shells are like this. It's pretty simple, 1, 2, 3, 4, 5, 6, so on and so forth. So it'd be 1s, and there's 2 electrons, and then 2s, 2, there's 2 electrons. Remember that there's 1 and 2. And then these P's are divided into 6. And then 3s2, and then 3p1. That would give you aluminum. And I'm going to show you a neat trick to figuring this out, okay? But go ahead and mark your periodic table up to show what I just showed for the most part, where your S, P, D, and F is, so that you can follow along in this lecture. Just make sure that whenever you come to your exam, you reprint a periodic table with no markings on it. Here's the periodic table that I was talking about, okay? And so I'm going to highlight here. This would all be S's. And then your P's are going to be these. Your D's are going to be, we'll do that color. Those are your D's. And remember, or recall that if you look back in the previous slide, your very first D's are going to be 3 D's. Your very first P's are going to be 2 P's. And then finally, your F's are down here for the purposes of this class, we'll rarely touch on these F's, just because it takes a very long time to solve those problems. You got to get all the way down there and account for everything previous. S, P, D, and F. So let's get started. So the electron configuration, as I told you, is a shorthand notation for the arrangement of electrons in an atom. Follow the trend of the periodic table going left to right, okay? The total number of electrons in your configuration should equal the total number of electrons for that atom, assuming that it's neutral. And you can actually add the electrons per subshell to get the total number of electrons for that particular shell. So let's practice, okay? And I want to show you a trick to begin with, okay? If ever you have trouble, here's the trick I do, okay? So I just draw 1, 2, 3, 4, and you can keep going, but for this class, you don't need to go any further than that. And then write 2, 3, 4, 5, and then write 3, 4, 5, and then a 4 and a 5, okay? And what you're going to do is right next to your 1, you're going to do your S's, and then your P's, then your D's, then your F's. So hopefully you followed how I did that. And here's how you're going to figure these out. You're just going to follow this rotation, start in the upper right and go through that first one. And then go next, and you'll notice you'll hit the 2S. Then you'll go through that diagonal, that diagonal, that diagonal. Okay, and that's exactly how you're going to solve these problems. And I'm going to show you this in actual practice. Let me just erase this. But I quickly drew out that little triangular looking diagram, and I'll show you how to do it. So hydrogen. Hydrogen's the very first element on the periodic table, located right here. And you'll notice that it's in the upper left-hand corner, so that's going to be the S subshell. And that each S subshell can only hold 2 electrons. But this one is not holding 2 electrons, is it? Because it's just the very first one going from left to right according to our rules. So hydrogen's real easy. You're only just going to put 1s1, and then you're done, knowing that that is your shell. So shell number 1, energy level 1. The S is your subshell, and then it has 1 electron in that subshell. Now, does that make sense? Well, it should, because hydrogen only has 1 electron because its atomic number is 1. So to be neutral, it must have 1 electron. And so we're just looking at a 1s1. But whenever you get to aluminum, it gets a little bit more complicated. Okay, now aluminum is right here. It's number 13. And so I'm going to show you to do aluminum using our trick. We just need to do it until we get to 13. So we go through with the 1s, and that should give us 2 because S subshells can only hold 2 electrons. Then we go through that, so now we're at 4 electrons. Okay, if you go through 2p, 2p is another 6 electrons. Remember, the p's can hold 6. And then you go through the 3s, which can hold 2. So right now we're at the 1s, 2, 2s, 2, 2p, 6. That gives you 10. You add the 2 3s's, that gets you at 12. Well, aluminum has 13, so we're going to stop right here at a 3p1. So if you just follow what I did, it was 1s2, because we filled that subshell, more than 2 electrons in aluminum, right? And then we said, if you follow that diagram, it tells you exactly what comes next. It was the 2s. Well, that one's filled, so then we continue on to the 2p, and p's can give you 6, but we still haven't met that 13 number, right? And so we continue on past the 2p6 to the 3s2, and then we finished off with the 3p1. Okay, now let's tally up our electron count and make sure that this equals 13. So that's 2, 3, 4. 4 plus 6 is 10. 11, 12, 13. And so that is the correct configuration of aluminum. If you wanted to actually see how that looks on the periodic table, what we did was, remember, we're going for aluminum right here at 13. So we said 1s, and there was 2 of them. 2s2, 2p6, you may notice 5, 6, 7, 8, 9, 10 is 6. Then we got to the level 3, S2, and then we got to the 3p1, okay? And so whichever method you like to use is fine with me. Okay, so you see how that would be a 3p, only 1. So let's go on to zinc. Zinc is located right here. It's a transition metal. Let me first erase some so we don't see as much going on. Here's zinc right here. It's a transition metal, number 30. Now, if you get good at this, you can quickly see that zinc is going to be a 3. Sorry. Let me go back here. It's going to be a 3D. Okay, so you may notice right here is like a 4s, but right next to the 4s is a 3D. So it's going to be one numerical digit below what the S was. Okay. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be a 3D10. So because we already know it's going to be a 3D10, let's use this little trick that I taught you to quickly get there. Okay. And then if you follow the trick, you see that the 3D winds up right here. Okay, so following what was done prior, you see that it's a 1s2, 2s2, 2p6, 3s2, 3p6. So we've already gotten further than aluminum. 4s2. And then according to this diagram, the very next one you go to is the 3D, and we found out that that was a 10. Now, zinc's atomic number you see is 30, so we should be able to tally these up and get 30. So 2, 3, 4, 10, 11, 12, 18, 19, 20. 20 plus 10 is 30, so we did this right. And go ahead and try cesium on your own, okay? Cesium is located right here in your alkali metals. So it's 55. So that one's going to be a pretty long one, and it might take you a little while to get there. Let me see. Of note, you don't need to really know this, but the electron configuration with every orbital filled, 118 electrons. It's this one. I've never even heard it said out loud. I guess it's oganesson, and it would read as follows. Now, I want to talk to you briefly about valence electrons. Valence electrons are the electrons found in the outermost shell. Remember, the shells were 1, 2, 3, 4. So the outermost would be the one furthest from the nucleus, and we define this as the outermost shell would be the one with the highest numbers. Okay. For alkali metals, there's 1 valence electron. For alkaline earth metals, 2. Halogens, 7. Noble gases, 8. And so let's take a look at how you can determine that really quickly. I would suggest on your periodic table, because we're not going to deal too much with transition metals in this class, go ahead and scratch those out. But your alkali metals, which are that column, they're only going to have 1 valence electron. Okay. Your alkaline earth metals are going to have 2 valence electrons. Okay, the column which has aluminum and boron is going to have 3 valence electrons. Okay. 4 with your carbon silicon row or column. 5 for your nitrogen column. Now we get to the oxygen. 6, the halogens, which is the fluorine, chlorine, bromine, iodine. 7, and then your noble gases, 8. Okay, that's a neat little trick to determine how many valence electrons there are. This is incredibly important because in the upcoming chapters we're going to talk about bonding, ionic bonds and covalent bonds. And in order to do that, you're going to need to quickly be able to know what the metals and nonmetals are on the periodic table. Keep in mind the metals are pretty much most of the periodic table on the left side. And this very small region over here are going to be your nonmetals. Okay. And keep in mind your semi-metals are touching that little staircase as shown right here on this diagram. So your semi-metals are going to be these. And let let me see something. Let me go back up here real quick because you can actually determine the number of valence electrons using electron configuration. So what you do is you find, let's take a look at hydrogen, right? There's only one shell, so you know it has one valence electron. And so you know it's going to be like hydrogen with one electron available for bonding. Whenever you look at aluminum, you can tell that the 1 and the 2 shells are going to be buried beneath this third shell right there. So in fact, aluminum, you can just circle the total number of electrons that are in shells that are the furthest from the nucleus, which is in this case 3. And so aluminum should have 3 valence electrons, 2 from the 3s orbital and 1 from the 3p. And that's exactly what you see according to this diagram. Aluminum's right here, and it has 3 according to that. Again, zinc is a little bit trickier because it's a transition metal. But whenever you get to cesium, you'll find that cesium has 1 valence electron. So I hope that makes sense. Get used to the terminology of valence electrons as we go on in this class. Have a great day.